Good evening. Welcome to the second session of Ellipse. In this session, we will discuss some more properties related to the position of point and also the auxiliary circle and parametric coordinates of ellipse. So let us go ahead. So we will now see the position of a point with respect to an ellipse. So position of a point with respect to an ellipse. With respect to an ellipse. So for example, here I have an ellipse and I also have a point right here. So imagine that this is my point P, say x1, y1. So first of all, we need to know that if I have an ellipse, then this region is called as the interior region. This is called as the interior region of ellipse. So interior region of ellipse. And this right here is called as the exterior region. Outside. Okay, so see, if I take this point here outside, I want to know here. So we need to get the condition. When would I say that my point P, say let P x comma y1, x1 comma y1 be any point in the xy plane. Be any point in the xy plane. And s is equal to x square over a square plus y square over b square is equal to, sorry, since I already have written s, so this is minus 1. I'm taking it to this side. This is the standard notation for s. Now I am saying that my point P is lying outside here. So as per our consideration, my point P is outside. So what should be the condition when my P is outside? So I'm just dropping a perpendicular. And now say when I drop this perpendicular, there will be some point here, say x1, comma, y, which is lying on the ellipse. So since x1, comma, y lies on the ellipse, so if it is lying on the ellipse, so this implies it will satisfy the equation of ellipse. So I'll be having x1 square over a square plus y square over b square is equal to 1. So from this I get y square over b square is equal to 1 minus x1 square over a square. This gives me y square is equal to b square into 1 minus x1 square by a square. I'll call this one. So this is my point y. So now if I talk in terms of height or use a magnitude of the height, then this height is definitely more than this height. This is quite visible by the common sense. So y1 is more than y. It's already taken point P outside. So if my point P is lying inside, then what would happen? In that case, my y will be more than y1. So it does not matter which ellipse you take. You can apply this. So y1 is more than y, which implies since I have to deal with y square, so I'll be squaring this. So y1 square will be definitely more than y square. Now, so y square I'll be just plugging here and compare. So y1 square is more than y1 is y is b square into 1 minus x1 by a square. So it's b square into 1 minus x1 square by a square. We can transfer this one here. So I have y square over b square is more than 1 minus x1 square over a square. Now I'll transfer this one to this side. So I'll be having y1 square by b square plus x1 square over a square is more than 1. So that is x1 square by a square plus y1 square by b square minus 1 is positive. This is nothing but s1. So conclusion is if s1 is positive, so s1 is positive implies p lies outside the ellipse. P lies outside the ellipse. And if my s2 is s1 is negative, so this implies p lies inside the ellipse. P lies inside the ellipse. And when s1 becomes 0, then P is on the ellipse. So P is on the ellipse. P is on the ellipse. This is what we have about the position of point with respect to an ellipse. Now, let us see the next part. That is, we now need to define the auxiliary circle because we want to get the parametric forms. So, auxiliary circle. Auxiliary circle is what? See, what do we need this auxiliary circle first of all? So, if you imagine that if I have a circle here, then I know the parametric forms here easily. That is nothing but r cos theta, comma r sin theta. These are the parametric forms for the standard circle having radius r centered at 0, 0. So this theta was nothing but the angle formed by this radial vector, we could say. This is theta. But for ellipse, it is not the same thing. For ellipse, it is not going to be same. For here, this is the angle, but I cannot write here theta because everywhere radius is different. So for that thing, what do we need? We need some another circle. With the help of this circle, now ellipse will shine. So consider how do we do it. Let me draw the diagram here first. By definition, a circle described considering major axis as diameter. Circle described considering major axis as diameter. And concentric with ellipse. And concentric with ellipse. That means what? If I have a circle here, okay. So if I have the ellipse here, then this vertex is basically a comma 0 by the very definition that we had given earlier, and this is minus a comma 0. This right here is 0 comma b, this is 0 comma minus b. So what we have taken is we have considered the major axis as diameter and we have described one circle. So if I consider then this is the major axis because here a is more than b. So if a is more than b, then major axis is 2a. So major axis is the diameter. That means equation of this circle. So if x square over a square plus y square over b square is equal to 1 for a more than b, then its auxiliary circle is we have considered this major axis to a diameter. That means its half is nothing but the radius. So x square plus y square is equal to a square. This is nothing but the auxiliary circle to this ellipse. Now, this auxiliary circle is not any ordinary circle that randomly one evening some random mathematics student or say faculty told this. A lot of work is being done on the auxiliary circle. Now let us see some of the beautiful properties. Okay, so we'll now talk about the eccentric angle here. Okay, so auxiliary circle we have found. So in the case, if you have the other ellipse, like let's say a is less than b, so in that case your auxiliary circle would be x square plus y square is equal to b square. Now, just take a look. So now if I consider, I'm talking about the eccentric angle first. So eccentric angle, say I'm saying theta. Now let there be a point P, say x1, y1. Or better, I won't take this. I'll take the parametric form of circle here. So suppose there is point P here, which is based on at r cos radius basically a. So I can remove this and write down just a cos theta. So it is a cos theta, comma a sin theta. This is my point P. Now, this is nothing but the vector radial angle. Theta is nothing but the angle which the radial vector of the auxiliary circle is making with the positive x-axis. Okay. So this is the radial angle here, theta. This theta is called as the eccentric angle here, basically, because now we are going to get the parametric forms using this theta. So this theta is basically not just on the ellipse, it's basically on the auxiliary circle of the given ellipse. So now I want to know what is this coordinate. So I'll just draw a perpendicular. So if I just draw perpendicular, then definitely I'm going to get a point on the ellipse. So let P, which is a cos theta, comma, a sin theta, be a point on the auxiliary circle of ellipse. Be a point on the auxiliary circle of ellipse. And P dash, which is a cos theta, comma, y, with a corresponding point on the ellipse. With a corresponding point on the ellipse. Why I'm saying corresponding point? Because if I take any theta here, like let's say for example, if I take this one here, then my radial vector will be now different and my theta will be formed here. Say like this, and I'll be getting the parametric coordinates here. So now you can work with any one of them. So I'd like to work with this now. So we can just plug it into the ellipse. So we have a square cos square theta by a square plus y square by b square is equal to 1. So a square gets cancelled. That means from here I get y square by b square is equal to 1 minus cos square theta. So I get y square by b square is equal to sin square theta. So y is equal to plus or minus b sin theta. So I get to know my y. So therefore, P dash is what? A cos theta, comma, B sin theta is any point on the ellipse. Is any point on the ellipse, basically. Or you could say that x is equal to A cos theta and y is equal to B sin theta. This is nothing but is a parametric form of ellipse. Is a parametric form of ellipse. So it's a parametric form of ellipse. Now, yes, we should not forget this, that theta belongs to what? 0 to 2 pi. It's called as the eccentric angle of ellipse. It's called as the eccentric angle of ellipse. Now, focal distance of a point on ellipse. Focal distance of a point on the ellipse. That means what? I have a point and it's on the ellipse. Let's say, for example, this is my point P. And I want to see what's the distance of this point from this focus. Focus S, this is A comma 0. This is S dash. A comma 0. This is A E comma 0. And this point is A by E. So since I want to find out SP is equal to what? So let P x1 y1 be a point on the ellipse. Be a point on the ellipse. I want to find out what is the distance SP. So by the focus directrix property, I'll be having SP is equal to eccentricity into PM. That means I'm finding this distance. So I want SP is equal to EPM. So E will be here only. I want to find out PM. So for PM, what we will do, I want to find out this distance, PM. So I'll just drop a perpendicular here. And then now we can see here, that means from this A over E, if I just subtract up to A, I'm done. From A by E, if I just subtract, I'm sorry, x1. then I get basically A minus E into x1. So this is going to be my SP, that is focal distance, and this is distance, so it should not be negative. So we'll consider the modulus. So therefore, SP is equal to mod of A minus E into x1. And if I have to find this distance, say S dash P, so they have to specify anyway. So now I want this distance. So when I am considering this foci, then now for my consideration, my point would be, my directrix would be that another one, not this directrix now. So if I want this S dash P, then for this thing, I'll be finding this distance, which is P M dash. So if it is required to find S dash P, then I'll be finding S dash P is equal to E P M dash. This distance I'll be having. Yeah, P M dash. So P M dash is again same. So from here to here, I know what is the distance. So from here to here, this is nothing but simply A by A in terms of distance. And then this point is simply x1. So if I just x1, I get my job done. So I'll be writing A into A by E plus x1. So this gives me A plus E x1 S dash P. Now from the focal distance also one can see clearly. Okay. Also SP plus S dash P is equal to A minus EX1 plus A plus EX1. So this gets cancelled and I get here 2A, which is nothing but the definition of ellipse. You got the focal distance of the point. Now in terms of parametric form also we can write down. So in terms of parametric form. So in terms of parametric form, I'll be having SP is equal to, let me not write SP. My point P is A cos theta, comma, B sin theta. So we know from here the parameter, this thing A cos theta, comma, B sin theta is any point on the ellipse. So that means if I take this point to be A cos theta, comma, B sin theta, so I found the distance here. So A minus E into x1 is going to be A cos theta. So I can write down SP is equal to A minus E into A cos theta, which can be written as A into 1 minus E cos theta. This is nothing but the focal distance. And for S dash P, I'll be writing here A plus E into A cos theta, which means I can take this A out and I'll be having 1 plus E cos theta. That's the focal distance from the other foci. We'll now be proving this property. Okay, very important. That circle described considering focal length as diameter touches the auxiliary circle. Let's prove. So basically, it is this. I have the ellipse here. Okay, let me draw a diagram. So here is the diagram. So now I'm taking P point to be A cos theta, comma B sin theta, B any point on the ellipse. B any point on the ellipse. Whose focal distance is SP. Whose focal distance is SP. Now this SP we have to consider as the diameter for this circle. Okay, the little circle which you see here. So now we have to prove that this circle and the auxiliary circle, they are always touching each other internally. So let's go ahead. So let P be any point. And now I need a SP. So a radius for this circle. So I'll be taking the radius for this little circle to be smaller, and radius for the big circle, we know it's already capital R, we can say. We already know this, but still. This is 0, comma 0. So this capital R is nothing but my auxiliary circle. So this is going to be A here. Radius is A. for the bigger circle. So radius of the smaller circle will be equal to what? SP by 2, because SP is the diameter. That means I need to find out SP. So SP distance will find out. SP is nothing but the focal distance of this point. So focal distance is, we have seen here SP is the focal distance. So we know it is going to be A into 1 minus E cos theta we can take. So A into 1 minus E cosine theta, this over 2. This turns out to be the radius of the smaller circle. Now I have to show that this circle touches the bigger circle. So basically we need the equation of the circle, or else condition for the two circles touching inside internally. Two circles touching each other internally. Touching each other internally. So the condition is nothing but the distance between the radii. So r minus capital R must be equal to the distance between their centers. C1 and C2. So that means now I need the center for this circle basically. Center for this circle is nothing but the midpoint of SP. So center for the little circle. So the center for, it's not little circle, I'm just naming it so that it is good for our understanding, because I'm finding the center for this little circle. So that is midpoint of S and P. So which I get here, the point P is A cos theta. So I'll be having here A plus A cos theta. So A plus A cos theta over 2, comma, this is going to be B sine theta plus 0 over 2. So B sine theta over 2. This is nothing but the center 1. And center 2 is nothing but 0, comma 0. We know it's the auxiliary circle, so center is 0, comma 0. So now we have to prove that the distance between the radii. So R minus capital R. Distance between the radii is nothing but R minus capital R. So this we know. Now, R minus capital R, if we see here, okay, so I'll just take the absolute value here. Now, just have a look. So R is nothing but this, minus capital R is simply A. So if I subtract this thing, then what do I get basically? So that is A minus, this is modulus, so no problem. So A into 1 minus E cos theta by 2, and then minus capital A. So this is this will turn out to be A over 2 minus A is minus A by 2. This is also minus, so I can take that minus outside, and this entire thing becomes plus. So 1 plus E into cos theta by 2. This is what I have. Now I have to prove that the distance between the two centers is nothing but this entire quantity. The distance between the centers we can now find out. So let's go ahead. This turns out to be A plus A cos theta by 2 minus 0 square plus B sine theta by 2 minus 0 square. This is the distance between their centers. So we can now go ahead, and for our convenience, I'll just take this A square over 4 outside completely, and I am now left with E square plus cos square theta plus 2E cos theta. So taking A square outside, and then from here I get B square over 4, and then it is sine square theta. Now let's see what do we get here. So we now need to simplify this expression. So you can take it to the next slide. Now we can find it. So this is A square over 4, and this is B square over 4. Means I can take 1 over 4 completely outside, so I get here half directly, and then square root of, now let's see here. So I have here A square E square plus a square cos square theta plus 2a square e cos theta plus b square sine square theta. So now if I consider a square e square, so we know what is a square e square. So square, or else wait a moment. The better idea would be to convert this b square sine square theta as 1 minus cos square theta. Can write down here 1 minus cos square theta. So now if I'm writing 1 minus cos square theta, which is same as writing b square minus b square cos theta minus b square cos square theta. Yes. So now what happens here is I can take a square cos square theta, this one and this one together. So I can take here a square e square plus a square minus b square would be common. Sorry, cos square theta would be common. So I'm left with here 2a square e into cos theta. Now, since eccentricity point of view, we know a square e square is equal to 1 minus b square a square. So I get a square e square is equal to a square minus b square. This quantity I can plug in here directly. So this will give me 1 over 2 and then square root of. So a square e square plus a square e square cos square theta plus 2a square e cos theta. Now, this is nothing but a square e square cos square theta. So a square e cos theta. So did I miss someone here? A square e square, that's fine. Because this looks like our goal is to get what? The perfect square rate for this thing. So I'll be having here a plus a e cos theta. So if I square this, I get a square plus a square e square cos square theta plus 2a square e cos theta. So only issue is this guy. Okay, I see that I missed this term here. So this is plus b square plus b square. I missed it. So b square now, if I take it here inside, then I know from here this equation that a square e square plus b square is nothing but a square. So that means I'll be writing this term plus this term as simply a square plus a square e square cos square theta plus 2a square e cos theta. And this is nothing but what we have written here, which is a square plus a square e square cos square theta plus 2a square e cos theta, which is nothing but square root of half of a plus a e cos theta. So we have proved that the difference between the radii is nothing but the distance between their centers. So this implies, okay, circle drawn considering focal distance as diameter, touches the auxiliary circle of the ellipse. The auxiliary circle of the ellipse. This is what we had to prove in this property. So hence we established the proof. Now let's go for the next property. Property number 2. So property number 2. Oh, we'll name it property number 1 because we have many properties in the way. Sorry, on the way. So the second property is the ratio of area of any triangle PQR inscribed in the ellipse and that of triangle found by the corresponding points on the auxiliary circle is nothing but the semi-minor axis over semi-major axis of the ellipse. Now let's see what happens here. Oh, sorry. This is not the correct form. Let me draw a diagram. So we can look at this diagram and now let's take PQR. So let P, taking A cos theta 1, comma B sine theta 1, and Q point to be A cos theta 2, B sin theta 2, and R is A cos theta 3, comma B sin theta 3, B, any 3 points on ellipse. So, uh, forming triangle PQR, and this point I have taken, see, this is P, Q, and R, and now I'm taking their corresponding points on the auxiliary circle. So for P I have A, and for Q I have B, for R I have C. So A point would be definitely A cos theta 1, comma A sin theta 1, and for Q I'm going to have A cos theta 2, comma A, sorry, A sin theta 2. And C point is A cos theta 3, comma A sin theta 3. Be their corresponding points on the auxiliary circle. If I'm finding this thing, so what do I need basically? So I just need the area of triangle. So the question is area of the triangle PQR inscribed in the ellipse, and that of triangle. That means we need area of triangle PQR over area of triangle ABC. So for this area, we can now just simply use the determinant. So it's going to be half of this determinant over half of this determinant. So here I just need to plug in all those points here. So I have A. Wait a moment, I think this is not enough. So the first determinant I'm writing here. So it's half of, I have here A cos theta 1, B sin theta 1, and A cos theta 2, B sin theta 2, A cos theta 3, B sin theta 3, and then 1, 1, 1. This determinant divided by half of this determinant, which is A cos theta 1, A sin theta 1, and A cos theta 2, A sin theta 2, A cos theta 3, A sin theta 3, and then 1, 1, 1. Now what happens is I can just cancel this half in half. And now if you see carefully, then first uh, from the first one, I can take A common. From the first column, I can take A common here, and I can take B common here. So I get here AB, and this gives the same determinant. After I take here A common from this and A common from this. So basically what happens, the two determinants also get cancelled. So I get AB over A square, which is B over A, and B over A can be written like this, 2B over. There's no point of writing 2B actually. Simply semi-major over semi-minor, or even if you could write major over minor, then still it's 2A over 2B, so 2 gets cancelled. So this is what we have to prove. Semi-minor axis over semi-major axis. Even if we write down their major axis over minor axis ratio, it would be still correct. We're moving to the next part. The next property would be the area of the greatest rectangle that can be described in the ellipse is 2AB simply. So of course we want to inscribe the greatest rectangle into this ellipse, so we have to take care of the symmetry. So let's say this is the one vertex of the rectangle. So I have here A cos theta, comma B sin theta. Now considering the symmetry, I'll find out the area of this little rectangle and I'll multiply by 4 because all of them have the same area. So area of the rectangle be 4 times the area of this little rectangle. So which is A cos theta, comma B sin theta. So this turns out to be A, B, I'll keep it here and then I'll write down 2 sin theta, comma cos theta. So this happens to be 2AB into sine of 2 theta. So which is max when sine 2 theta is equal to 1. So therefore, max area would be 2AB. Okay. So that's all in this session. We'll see you again with the tangency in the next session. Thank you so much.